Customer service. We're going to record to the cloud. Welcome everyone to our seminar. Hi, everyone on YouTube, everybody on Zoom. Get started in just a second. Any announcements?
There's actually anybody that's interested in the Wetlands Club. It's been kind of in an absentee state for a little while, but they are going to have a meeting this evening, 5 o'clock, room 3177, McCarty Hall A. So if you're interested at all to figure out what is going to happen or find out that really nothing's going to happen, just show up. We're gonna have pizza. So 5 o'clock this evening, 3177.
All right. Any other announcements? Any other stuff going on out there in the world? No? All right, well then, let me just make sure the YouTube stream is streaming. Let's see. Yes, YouTube is good. Excellent. All right, so thank you very much for coming. Today is Water, Wetlands, and Watershed Seminar. It's fall 2024. And today we have Dr. Alberto Crassostrea. Dr. Crassostrea is an assistant professor, but not for much longer. He's soon to be an associate professor with hopefully at the University of Florida here in the Civil and Coastal Engineering Department. He specializes in the dynamics of coastal environments, particularly estuaries, tidal channels, and salt marshes. His research combines numerical modeling, field data, and I think probably some machine learning and some other kind of approaches now. He's been working lately, especially on nature-based solutions. So this idea of combining natural and built environment for coastal protection. And his dedication to coastal management is further reflected in his leadership of international collaborations, contributing to global efforts to mitigate the impacts of climate change on coastal ecosystems. So we're going to hear about, is this a Dali?
GTM. Have you ever been there?
No, there's a real place?
No, it's not.
No, I don't recognize the hills in Florida, so. Okay, so tell us about this, Dr. Crassostrea.
Thank you for inviting me today. Like 95% of the talks I attended over the past weeks always started with an AI picture, and I never did it. And today is like, let's try an AI picture myself. Why everyone does it, I don't do it. And then I asked like GTM estuary, boat wakes, an oyster reef, and he came up with this. You almost fell for it, but
It's not very,
yeah.
Doesn't look like Florida, right?
Yeah, there's not much Florida, but yeah, I should have Florida. I'll try next time. Anyways, today we're gonna talk about how boat wakes dictate bank erosion and how this affects filtration services in a small patch estuary. I'm presenting today, but I wouldn't be presenting today if there was I didn't have the help of Daniele Pinton. I supervised him as a PhD student. What you see today is part of his PhD dissertation and part of the work that he's doing now, working with me as a postdoc. So all of you, at least most of you, know everything about oysters and reefs, but I'm just gonna go over the basics now with you. So an oyster reef is a dense structured habitat formed by oyster that cluster together, often in intertidal, subtidal zones. So you can see on the left an oyster reef flanking a mangrove forest. On the right, you have an oyster reef on a tidal flat. You can see that is the plot where you can usually put an oyster reef to collect information inside the plot, such as the size of the oyster, the number of oyster per plot, etc. Today we're mostly focusing on the eastern oyster, Crassostrea virginica, which is native to the Atlantic and Gulf Coast of North America. You can see it here on the right picture. So oyster reefs provide not only protective, but also non-protective services. So protective services are services that help shield the coast from natural events. So one typical protective service is coastal erosion control. So oyster reefs dissipate waves. So if you have less waves impacting the bank, you have a smaller energy of the wave on the bank, so less erosion of the bank. Also, with less waves, you have less flooding behind the oyster reef. Also, they filtrate the water, so they purify the water. They provide habitat for marine species. So they increase biodiversity and they can possibly also sequester carbon. I heard it's not my field, I heard there's a lot of debate if actually they sequester or they don't sequester carbon, but that's one of the possible protective services. As for non-protective services, they support fisheries, they provide recreational opportunities, they have a lot of cultural and economic value, they recycle, cycling, and they're also a food source. So here on the right, you see this image, and I really like it. Shows the difference in water clarity for the same water sample collected in an estuary when you don't have oysters and when you have oysters. So you see how they filter out the suspension very efficiently. So if you want to talk a little bit more about the filtration services, so how does it work? So oysters are filter feeders. So they filter water out from the water column. So, and everything that is in the water column, so such as phytoplankton, particles, so the nutrients in the water column, part of that is assimilated. So it helps with the growth of the tissue of the oyster. Part of that is released as feces and pseudofeces. Therefore, you are left with more clean water. A single oyster can filter up to 50 gallons of water per day, thus improving water clarity, as you said. And filtration can really help to keep an ecosystem balanced because it can control, by removing this material here, it can control algal blooms and promote biodiversity. When this material becomes too concentrated, you can have these algal blooms that basically trigger the death of different species in the estuary. Last decades, and we saw loss of oyster reefs. So all around the world, oyster reefs number and density of oysters within an oyster reef is decreasing. So what are the possible threats to oyster reefs? So we have coastal development, pollution, overharvesting, diseases, and also climate change. They all can reduce the number and density in oyster reefs. This is just an example from the Guana-Tolomato-Matanzas estuary. So you see the red polygons indicate dead reefs, while the green polygons indicate live reefs. So there is a certain percentage of reefs are actually dead. And lately, in the past years, there's a lot of discussion about the impact of boat wakes. So in this waterway, you can see here, there are boats traveling every day. And boat wakes generate wave energy. This high energy can lead to the decline in oyster population because they can prevent larvae settling. So for this oyster reef to survive in time, they need to recruit larvae. They spawn, they release larvae, they move around with the water, and these larvae have some chemical clue, and whenever they float on top of the reef, they settle on the reef. Well, if the turbulence of the water is too high, so if there's a lot of wind waves, also tidal currents, these larvae cannot settle as pets, okay? And both ways can also dislodge oysters or damage reef structures. Finally, they can erode sediments around the reef that increase the water depth, that can increase the waves and the tidal current, so it could lead to destruction of the reef. What's the consequence of this decline of the reef's number? Well, as we saw before, we lose all those services, in particular, filtration services, since this presentation is about those, and we have loss, you have a worsening of water quality, and we can also have loss of habitat and loss of marsh bank protection. Okay, let's do a slide. So for this talk, we have three main objectives. The first objective is to understand how location of oyster reefs affects estuary filtration services. The second objective, we want to assess the impact of bank erosion on oyster reef mortality. Finally, we want to determine the relative impact of both waves and wind-generated waves on reef mortality. So we'll start with the first objective.
You might need to go to the, keyboard.
Or utility where hiding the.
Ah, you gotta
So
click
have to
back on the
click-
screen. If you click just the mouse onto the screen, then you should be okay. Because you,
Okay,
because of Zoom.
that's why.
Yeah, he's
We have
got that.
three publications.
Yeah. Yeah, now the clicker should work again.
All right, so we start with the first objective. We'll understand how location of oyster reefs affect estuary filtration services. So the study area is the Guana-Tolomato-Matanzas estuary located close to St. Augustine. This is a drawing of the study area. In black, you see the boundary of the reserve up here and up here. In blue, you see the water body. That's part of the intracoastal waterway, so a lot of boat traffic going up and down this waterway. These are the polygons that indicate live reefs on the left and dead reefs on the right. The Fish and Wildlife Research Institute found that 4,800 reefs have live oysters, while 400 reefs have dead oysters. So we're talking about 10%. So for this estuary, we need an allometric function for oyster dry tissue weight as a function of shell length. The fact is, it's much faster to measure the size of an oyster than computing the dry tissue weight, because for computed dry tissue weight, you gotta, go to the field, get the oysters, bring them back to the lab, shock them, put them in the oven, let them dry for many hours. So it's a lot of work. So shell length is easier to measure. So our coder, Dr. Markham, did this for 21 reefs and 30 oyster over 10 size classes per reef, took them to the lab, measured dry weight for each oyster, measure of course also the length of the oyster, and he came up with this plot. So dry tissue weight over shell height. So there is a basically power law, shell length to 1.9 almost, okay? Then we have 250 reefs surveyed by GTM over about 9 years, and they collected oyster density, shell length, and what we did was performing inverse distance weighting interpolation. So from those 250 reefs, we computed density and length over all the 4,000 reefs. Okay, so once we have these, we can compute the dry tissue weight for each oyster reef from the length of the oyster. So here is the numerical model I've used to compute the filtration services of the estuary. On the left, you see the boundary of the model, the different stations used for prescribing boundary conditions in the model. On the right, you see the type of boundary conditions. So offshore, I prescribe the tide. The red squares are the temperature time series from the NCOM model, is a global oceanographic model. Then in blue, we have the temperature and water time series from the NER station. And in purple, we have water data from the NER station that is right here. Then we have finally temperature and water level time series from FTP and discharge from the NER. So discharge is here at Palliser Creek and temperature are here. So this is the bathymetry, has been collected over years with different methods, topography LiDAR, boat service with an ADCP. Data have been put all together, read by the model. And then we compute the hydrodynamics over the entire estuary. So we prescribe this tide in and out of the estuary. So we can run the model, compute velocities at each location of the estuary, at each point in the vertical, and also water level. With this hydrodynamic field, we force a particle tracking simulation. So we release particles, and I share the video so you can understand how this works. You release particles in the estuary. So we use as injection points a regular grid 50 meter by 50 meter, only the wet areas of the domain. And we use 6 injections, 1 every 2 hours. Up to this point, we don't perform any filtration service. We're just like running this model and moving particles around. We ran this simulation for 1 month between May and June 2018 with 1 minute timestamp. Now we're getting to the filtration services. So how do we compute those? So you saw all those particles, right? So let's assume we have a particle passing here through this area. Every time the particle goes above an oyster reef, we filter out the particle, pretty straightforward. Each particle is initialized with the mass M proportional to the water depth at the injection point. Why that? Well, if it's proportional to the water depth, that means we have a concentration that is uniform over the domain. We try also to initialize a uniform number of particles over domain, that means non-uniform concentration, and the results were not really different. So we stuck with this, but you can do it either way, didn't affect the result. At each time step, we reduce the mass M of the particle by this factor, by this value dm, which is proportional to the filtration rate of the oyster reef. So we assume there is no increase of mass in time. And how do we compute this filtration rate? Well, it's the volume of seawater filtered per unit time by each reef. So we have liters per hours. So that's going to be a function of the filtration rate of a single oyster. And of course, in a reef, you have many oysters. So you cannot only multiply by the area of the reef. Of course, you need also the density of the oyster. So let's say there are 70 oysters per square meter. You multiply by the number of square meters, so 100, you get 7,000 oysters, and you multiply by the filtration rate of each oyster, so you have the total filtration rate of the reef. So this is filtration rate, FR, and then subscript reef. Okay, I don't want you to get confused. So this is filtration rate, oyster, 1 oyster, okay? O is always little type.
Okay.
Okay. So how do we compute this filtration rate of the oyster? Well, there is this guy. The first Serpentol proposed a relationship. It was improved by Zur and Gassen. He showed that it is proportional to the dry tissue weight, to the 0.58, and there is a factor that takes into account of the temperature. So for a temperature in Celsius degrees, of 27, this is maximum. If you have a larger temperatures or lower temperature, the oyster filters less. Okay, so there's a maximum filtration rate of a single oyster at 27 Celsius degrees.
That's regardless of the concentration of particles or food, and it's just,
Yes.
it's purely a liquid pumping.
It's pumping
machine.
of liters of water. Okay?
Yeah. Okay.
So the first step we did was plotting, the estuarine residence time. So if we let this particle goes, back and forth with the tide, these particles slowly exit from the domain through the inlets. We didn't apply any filtration services here. We just wanted to see how long it takes for the estuary to release particles, okay? So the residence time has been defined as the time it takes for the number of particles to reduce by 1 over E, where E is 2.7. It's one of the many definitions of estuarine residence time. So it takes about 12.6 days to reduce the number of particles by 1 over 8. When we activate filtration, we found out that oyster reefs remove about 60% of the particle mass during an estuary residence time, which is a number pretty significant. Previous studies for different estuaries found values between 10, 20, 30%. So these, we're now doing a literature review to have this comparison done. But a quick look shows like a lower number. So this is a very pristine estuary. There are many oyster reefs. despite the fact that some reefs, like 10% now, are dying, there's still so many reefs around, they filter a lot of particles. I also want to know that 20% of the pollutant exit the estuary before being fully filtered by the oyster reefs. That means I start with a mass, let's say 1, 0.2 exit the estuary, 0.6 is removed by the oysters. So this is a comparison that I made for the filtration reef rate of a reef. I didn't make a comparison for the global all estuary, but I did it for per reef. So the GTM estuary filters 4,000 liters per hour per square meter. As a comparison, the Gulf of Mexico filter between 40 and 154. So we're talking like 10 to 30 times less. So order of magnitude, okay? This low value in the Gulf of Mexico has been attributed to low density of those reefs. So they have about 400 individuals, 700 individuals per square meter, while we got 1,400 to 3,000 per square meter. It's a lot, 3,000 individuals per square meter. Chesapeake Bay, for pre-colonial reefs, in which oyster population density is comparable with those observed now in the GTM estuary, we are around the same value. So it seems that the GTM is doing well. Although there's like development around and we are losing oyster reefs here and there, it's still doing great. Now I want to show you how the oyster reef filtration rate changes in a direction cross-sectional to the bank, okay? So this is average over the entire estuary. So for all the banks, every about 50 meters, we computed this value. So here at 0, you are at the bank. For positive values, you're away from the bank landward, okay? So you see there is a peak of filtration services here at the bank, and then this value decreases, and then you have a slight increase toward the end. I want to point out that the way I plotted this is filtration services of a reef per unit of weight. Because we said that you can't really say this reef filters more than the other one. Well, this reef is huge, this is tiny, of course it's filtering more. And you cannot even say, like you have to say per unit of dry weight because the density can be different in the two reef, right? So the only way to compare a reef with a reef is going per unit of dry weight, because there could be 1,000 kilograms of oysters in one reef and 1 kilogram in the other reef. So to make it comparable per unit of gram, you have these filtration services, okay? So why do we have this behavior? Well, the number of particles computed by my model and plotted here exponentially decreases away from the riverbed. You have many more particles. These are the number of particles entering a cell of the model at different distances from the bed. This is resident time. We know the resident time farther away from the channel is higher. The flow velocity is smaller, particles hang out there more. While resident time is smaller because the velocity is higher closer to the bank. So this is a typical behavior of resident time. What we're seeing here is that what matters much more is the fact that you have many particles entering here. And that triggers this overall peak of filtration close to the bank. Resident time, yes, does increase a little bit, things toward the end, but not a lot, okay? So it's almost negligible compared to the path that the particles follow. And I have this video that explains this if you guys are a little bit confused. So in the first scenario, we have uniform tidal velocity over the intertidal region. You have uniform filtration rates, and let's assume we filtrate with each oyster reef, those 5 blue squares are oyster reefs. So let's assume the oyster reefs, they all have the same size, same density of oysters. Let's start simple. Each filters 40% of the mass of the particle that enters into them, over them. Okay, so the particle entering with a tide and exiting, So I'm tracking right here how much is filtered. Okay? So since this guy is right where the particle is coming, it's filtering more. So with time, you see this curve, you get the behavior I showed before. Now,
That particle is representing many particles, right? Yeah.
yeah, this is like every time I'm actually resetting the mass of the particle, you can do it even without resetting. It's just like it will finish right away. So to make the video longer, I just send a particle, and then let's say exit with 0.05 mass, and then I send another one with 1.
Yeah.
Okay, but it works either way. You just don't want to have the video going. And then this is just like to show the count. And it has a second effect. We can show from 2D simulation that not all the particles reach the end. So if I run a model simulation, some particles stop before, some particles reach the end. So if you add this to this, it amplifies the effect. So there are two important factors. Well, you are in a privileged situation in front of the bank. And if the particle travels back and forth from the beginning to the end, you win. But you win even more because the particle not always travel to the end. So if you put the two things together, you get something like this, right? It's even more peaked. Compare the numbers, 404 to 246. Look at the ratio between these. This is like not even double. Here we're already like almost 3 times. Okay? 300, 100. You see? Because some particles just stop here. Okay? Well, that's not all. Here, I assume uniform tidal velocity. So resident time is the same everywhere. Now, if we assume a linear variation resident time increasing toward the end of the marsh, we get that for video. I didn't put like a large variation, but what you see with this video is that the point on the right is actually slowly getting a little bit higher because the particle here hangs out a little bit more. So you see when the particle gets all the way to the end, it hangs out a little bit more and it helps increasing this value. So after many iterations, you get that curve that I showed you before with a slightly increase of filtration toward the end. You barely see it here. You probably need to run one with a, you see it here, 21, 18. Okay, it is higher. Then you can change, depending on which marsh you're working on, like if the resident time much larger here than here, you get a larger peak. So this is basically what we showed in the previous slide. Okay. So the main findings here are oyster reefs in our estuary play a crucial role in water filtration, cleaning about 60% of the water volume during an estuary resident time. The model shows the downstream effects. We gave a name to this process in the paper, downstream effects. If you're in front of a road of oysters, you're in a privileged situation, okay? You filter more. So we call that downstream effect. Create a spatial gradient in the concentration of pollutants with larger concentration close to the main channels and lower concentration further away. So downstream effects is dry spatial variation in filtration services. Local resident time does not have a strong impact. I was there trying to zoom in and see the effect. Okay, so everyone say, oh yeah, oyster reef filters more if the resident time is higher. Well, it's not really true. Like it really matters much more. Hydrodynamics matter. How particles move around, how matters move around is more important than the resident time itself. That's the message. Now, we want to assess the impact of bank erosion on oyster reef mortality. So we got a bunch of satellite images from 2006 to 2023. So one USGS, 2 from NOAA. These are the 3 different images. We, with an image recognition algorithm, we detect the bank. And then if I put everything together, you see that there's been an erosion from 2006 to 2023. We did this over the entire estuary. And we see there is a lot of variability. So lower than 0 is erosion, larger than 0 is accretion. There was more, the value of the median erosion is larger in the if you consider the entire data set than if you use the older data set. So we have 3.30 meter of erosion, 2006, 2015, and it becomes minus 8.30 for the entire range. So there seems to be an increase in erosion. On average, we have 0.3 meter per year in this time range and 0.5 in this time range. Okay, so we first estimated the erosion. Then, how is this erosion affecting oyster reefs? Well, you can be in a situation like this, which have an oyster reef close to the bank. If the bank moves, then you can have oyster reef mortality. You can have in a situation like this, in which you have oyster reef, and then you have that reef has already been, already died like in the past, and then the bank moves. Okay, this is an image, sorry, of the oyster rate. So this case here is a case in which you have dead oyster reefs, and the waves basically keep moving this rate above the land. And as this process continues, you can impact the live oysters. And here is another situation in which you have some dead reefs here. You have a secondary channel here. And again, if you move your bank, you can start impact live oysters. So these are different situations which if you move the bank, you can impact oysters. So what did we do? So this is the present day bank. We assume progressive erosion, and we progressively remove oyster reefs away from the bank. Every time we remove the oyster reefs, we rerun the model and we recompute filtration services. And that's what we get. So present day situation, yellow, filtration only from reefs with live oyster population. If we add the dead ones, so if we assume that actually dead are alive, we have an increase of about 0.8, that in percentage is about 16% improvement in filtration. So those dead oyster reefs were good. We're missing out. Now, as we erode the bank, these filtration rates drop fast. Why that? Well, we saw before that our filtration services per unit of gram of oyster are large here. On top of that, the previous animation was fancy, but was only 1D. In 2D, you have a variation of area of reefs. So you have more reefs closer to the bank, and then the more far away you go, you have less reefs. So by putting these and these together, you have even a bigger peak. So you're missing out, you're losing some filtration services if you erode the bank, because these guys close to the bank filter a lot. So the main finding again, we have an average 0.5 meter per year of bank erosion, and this will cause a 20% decrease in filtration services if bank erosion does not accelerate. I didn't point it out, but look at this line. If you have 0.5 per year over 1 year, you have about 50 meters here, right here. You have a decrease of 0.1 that in percentage is 20%. And then as we showed, FS reduces exponentially because of bank erosion, and is due both to the reduction in area away from the bank and to the removal of reefs with more filtration services. So the final objective, now we saw these fancy results, but what about both ways? So can we tell if there is an impact of these both ways on reef mortality? So we came up with computing wind waves and both waves and comparing them with each other. So we first compute wind waves. We designed this model. It's a wind wave generator. We identified a fetch direction. So we start from the reef and we go in a direction until we touch the land. Okay? And this distance is the fetch. The larger the fetch, the more the time wind acts on the surface and the higher the wind waves. We started bathymetry along the fetch from the DM. We extracted wind data from the Palliser Creek meteor station. This gives an idea of the frequency and many occurrences of wind in this direction, but the colors is what matters most. You have a higher wind in this direction, and higher wind generates bigger waves, okay? Frequent low wind doesn't really create many waves. I can have low wind every day, you're not gonna see waves. But you can have a day with a big storm, you see huge waves. Okay, that matters most. So this is the principal wind direction, and we plot all these in a 1D model for wave generation, propagation, and dissipation. So you have like it's an unsteady PDE partial differential equation with some source terms that takes into account all the main processes that change the wave height, which is bottom friction, wide capping, and depth induced breaking. And there's of course a wind term that is proportional to the square of the velocity of the wind. Okay, that's the generation term. This indicates, should be plus here, what we show in this equation is basically that at equilibrium, when wind generation is equal to the dissipative term, you get the actual equilibrium wave height. Okay, so wind blows, it increases the wave height, but then the bigger the wave height, the bigger the dissipation, up to a point in which you get your equilibrium wave height. Okay, so it doesn't matter if the fetch is actually longer. At that point, doesn't matter. You got a fixed value and it's the same. So we compute energy from a typical equation for wave energies proportional to the square of the wave height. And then we compute the wave period from an empirical equation specifically designed for estuaries, not for open ocean. Then we have this fancy database from the automatic identification system data set. And this is the entire US, and we focus on the GTM NER. These are collected by the US Coast Guard, and basically boats have a GPS in it. So you're tracking the position of the boat in time at a pretty high frequencies, sometimes like 30 seconds, 1 minute. And these data contain the location and time I said, and the type of vessel. Is it a planing boat? Is it like another type of boat? Is it displacement boat? What's the speed of the boat? You can compute it by time and location, of course. So you know also the length of the boat, the beam, and the draft. The beam is the width of the boat. The problem is not all the boats have a length in the database. That's the problem. So and not all the boats have displacement, but we have a lot of length, about like 60–70% of the boats have a length, but displacement is probably 5%. So we need to create a length displacement relationship. So we divide for different type of boats and we create a regression. For these guys, we cannot create a regression because we have only 3 points. These guys, all the points are pretty close to each other. So what we did for those cases, we took the entire database of the US and then we fill out the gap. That's the best we can do. For boats for which we have length and not displacement, we're going to use this regression curve. For both that you don't have neither length nor displacement, well, we're going to just follow the probability distribution of the length that we extract the probability distribution, a value of the length from the distribution. So real quick about the different modes at which a boat can travel and a different type of boats. These are planing boats. They can plane in the water. So in displacement mode, when they go at low speed, waves are small. If it accelerates, moderate speed, you have larger waves. At some point, the speed is so large that the lift compensates for the weight of the boat and it brings the boat up and it goes in plane mode. At that situation, at that instance, the displacement is smaller, so you have moderate waves. On the other hand, big displacement boats have a monotonic increase of wave height with the speed. You increase the speed, these guys are never planing, they're too big. So why is it important? Well, we need to distinguish between the two because if a boat is going very fast, it's not always bad. If it's a planing boat, it's actually making less waves when it's going fast. So we need to distinguish between the two. So we detect the path of the boat, the average path of the boat. We make sure that it passes through the boats we see in satellite images, which is encouraging. And then we use for the wave height literature equation. Maynard proposed this behavior with wave height and speed for a planing boat, but when it's not planing, the behavior is like this. So this is for displacement vessel. Maynard also provides this range for a crude number to go from one regime to the other one. We decide to use the displacement for number. So it's the velocity divided the square root of gravity times the 1/3 of the displacement. Okay, the displacement is the volume of water displaced by the boat. You take 1/3, you get a length scale. Okay, so this allows me to go between these regimes for planing boat, because displacement boat, those big guys, always stays in displacement. Okay. And then we use this equation for displacement mode, plane mode. And the main idea is that, look at the red term. This term indicates like a decrease in wave height away from the boat. That's what usually happens. The boat creates a wave. If you've ever been like next to a boat moving an estuary, you see that it's pretty big next to the boat, and then it progressively decreases away from the boat. This is mostly due to wave dispersion. It's a very nonlinear wave. The different sinusoidal component of the wave travel at different speeds, so they separate, and the significant wave, the average wave height, I would say, of the train of wave is decreasing in space. When it gets to shallow water, they still travel at the same speed. So the wave height can only decrease a little bit because of friction, but it's not as big as this decrease. So here is the result. So here we plot wind waves, so energy, for live oysters and for dead oysters. So for each oyster reef in the domain, we have the energy because we computed it with our models, so we can make a comparison. So we can see that for dead oyster reef, also for wind waves, you have a larger value of energy than for live oyster reef. But this difference is much larger for both waves. So wind waves seem to have an impact, but the impact is much bigger for both waves. So you have like almost the double of the median here of the value of the energy. Okay. How can we also plot this? Well, we can also plot the probability distribution of live and dead reef area. So live area in blue, so the sum of all these blue rectangular is 1, and the same for the sum of these red rectangular. So this is a probability distribution as a function of what, like of energy. Okay, so we see that for larger energy, also for wind waves, you go from having a lot of live oysters to having more dead oysters. But the amount of oysters, of dead oysters you have here for both wakes, for larger energy of the both wakes, is much bigger. These regions which have live oysters mostly where you don't have boat wakes and no wind waves. So like lateral channels, you don't really have boat going there. You don't really have fetch because there are small lateral channels. We can also plot the cumulative function, cumulative distribution. So dead oysters divided by the sum of the dead oysters over the entire domain. And we do it as a function of energy of the wakes over energy of the waves. So when that's 1, the energy of the wakes is more than the energy of the waves, right here. So here we have larger waves. On the right, we have larger wakes. So you can see that up to the point in which the waves energy is equal to the wake energy, you only have about 25–27% of the total dead oyster reef in entire domain. You need to move in the domain in which you have larger wakes to have more oyster reef, so to have the biggest percentage of total dead reefs in the estuary. Okay, so only 27% here, and 73% are located where waves energy is larger than wave energy. So this showed that the waves have a strong impact. If you have a larger wave energy than wave energy, you're more likely to have dead reefs. So summarizing, we said that the energy is 90% larger for the both wakes than the wind-generated waves. Both wakes have a larger impact on oyster reef mortality than wind-generated waves. So the overall conclusions are the following. So large boat wake energy increases the likelihood that a reef dies. Boat wakes mostly impact reefs that are close to the bank of the waterways, which are the reefs that filter the most. We saw those nice videos that explain the process. And this causes a sharp decrease in filtration strategies. So a consequence of this is that if oyster restoration is planned, the position where the reef is restored does matter for filtration services. You don't want to restore an oyster reef if the purpose of the restoration is water quality. You don't want to restore an oyster reef when there's not much filtration. So you want to make sure you run a model, you see where filtration possibly is larger, and you want to put the oyster reef where they can actually filter, if that's the purpose. If the purpose is like protection of preventing erosion, then you make that the main focus. I want to prevent erosion, I put it there. But then it happens that if you put the oyster reef close to the bank, you're both protecting the bank and filtering the most. So it seems like the sweet spot there. And we're currently working on providing quantitative direct link between bank erosion and both wakes. We actually didn't do that direct link yet. Okay, we saw bank erosion causes a reduction in filtration services. We showed that both wakes causes dead oyster reefs, but we didn't show that both wakes cause bank erosion. So we're working on that. And with that, I'm done. These are a couple of papers, and we have one that is almost submitted, but most of the stuff, the first two objectives are here, and you'll see soon the third objective. And I want to thank also the authors and collaborators that helped me with this project. Thank you very much.
Thank you, Alberto. We'll go questions in the room first, and then see if we have any on YouTube or Zoom. So from students in the room.
So if you're doing restoration, but you're worried that there's current boat wakes, where would you be able to put the reefs that it doesn't die while it's being restored?
That's a very, very good question. I don't have an answer to that. That's like that's a very good question. So like you're saying, well, there's a lot of wave energy. I'm putting the restored reef, but you just said the wind waves are killing the reef. So how are we solving that? Well, there's a lot of research trying to to understand if the angle of the reef with respect with the waves matter, for example. Another thing is like the width of the reef. So if you have a larger width, then you dissipate the waves more. So maybe you lose slowly the front part of the reef, but then it's gonna take so long for the entire reef to disappear. So you can play with the shape, the width of the reef. You cannot play a lot with the vertical elevation of the reef, because if it's a natural reef, oyster reef don't really grow above sea level. So ideally, you would love to have a breakwater, natural breakwater made of oyster reef that goes up plus 50 centimeters above sea level, but they don't live there, right? So you can't really play much at equilibrium with the vertical aspect, but you can play with the angle and the width. And people are really trying to understand how you can put the oyster reef there, survive the wakes, protect the bank, and increase filtration service. That's everything.
All right, so Alberto, what do you think about the estimate that the oyster pumping rate is a constant that is not a function of the concentration of food? In other words, the filtration rate is kept as a constant, right? It's a liters per hour per oyster per square meter. But for example, like when we go eat, right? Like, we eat for like an hour if it's a small amount of food. But if it's like we chomp really fast and we're done, we stop filtering, right? So
Yeah.
like if there's plenty of food, if there's and especially if you have this benefit of being kind of near the front, like near the front, you maybe only have to filter at a lower rate, and then near the back, you filter. Maybe it all works out in terms of particle filtration, but
Yeah, so I'm not a biologist, but what David is asking is a very legit question, like, is there a threshold? Like, by reviewing the literature and by reviewing the 2013 paper, there is some spreading data, but it seems to be a pretty much like proportional relationship, and there's not a threshold back there.
that like the mass of the oyster is a great predictor of its
They're very,
filtration
very
volume.
hungry. They're very hungry. But like, it's still like a question among biologists. Is there a limit? Or they keep eating? Well, the more they show in those papers that the more they eat, the faster they grow.
Well.
So, and that's obvious,
At
right?
some point, right?
But,
Yeah.
and the bigger they are, the more they eat. So is that like stopping at some point? Like data doesn't show that. Like lab data also collecting oysters, bring them in the lab, it doesn't show that threshold.
Mhm.
So I'm not a biologist. I know people are still researching that, but it's a valid question. As of now, there's no evidence of a threshold.
It'd be interesting, just because you have some filtration rates, if you have a certain concentration, what would the mass of the particulates be divided by the number of oysters? And do you fill up, I mean, what's the gut capacity of an oyster? I mean, just as a back of the
Yeah.
envelope start.
Yeah,
I do have a question though, with regards to, there's a correlation here between dead reefs and wave energy characteristics. But do we know that that's the causal mechanism, or is there something else perhaps at play that might initially cause the reef to decline, which then increases its vulnerability specifically to boat wakes because they're different energy and character, but
yeah,
is,
it's a great question. So we're also looking into that. So there is like this idea that maybe harvesting might affect that. So if there's over harvesting, so you remove many oysters, and then there are boat wakes, maybe the oyster reef is more likely to die. So that we're trying to run an our population model and changing the rates at which you remove oyster reef through harvesting and prescribing some boat wakes. So you have the shear stress of the boat wakes, you put a threshold on larvae settlement, so you put an actual mechanical erosion on the oyster reef, and you try to come up with an equilibrium. And there is some evidence from the preliminary simulation that Danielle is running that actually there is a threshold for harvesting above which the reef cannot keep up with the wakes anymore. With the small wakes, it can keep up because you're removing oysters and you actually have more area for settlement for spats. So in the model, and model is like trained with the actual data, every time you erode some oyster, you remove some oyster, then you have so much space and all these spots settle down. But then when the shear stress is so high, then less larvae settle, and then it's a runaway erosion. So that's how we see it now with the model. I gave away your idea.
One last question.
I think it's gonna do it.
I know you said you're not a biologist, but does temperature play a role in that potentially too? Like, I know you said that there's a limit for filtration based on temperature, but does that increase vulnerability of oysters too and potentially like make them more vulnerable to boat wakes?
Yes, yeah, that's a great point. So temperature and salinity really affect oyster quality of life.
Okay.
So they have an optimal range in temperature, optimal range in salinity to survive. So there is no evidence that in the past 10 years, temperature and salinity changed by a lot. I mean, there are some percent changes, of course, climate change is there, temperature of the ocean is a bit like increasing, and then of the air, but those are not large enough to trigger oyster reef in the opinion of people I spoke with, biologists that are studying this. So it's a great point. I see that as a more of a long, like a time scale effect. So in the long term, like with a large change in temperature, you can actually kill the oysters, and with big shifts in salinity,
Yeah.
right? If you change if you have a dam, you remove the dam, and you have more fresh water coming the estuary, then you could reach that point in which oyster reef don't grow anymore. So yeah, another good question.
Sorry. In the slide 16, you show that the filtration of the reef near the deep water is more than shallow water.
Dimensions. All right, 16.
Yes. The reef near the deep water can filtrate more than the far from the deep. it means they are fed more than others, and they can grow more.
Yeah.
Okay, but on the other side, there is a way more at that side and can
Yeah.
be killed. Okay, in the reality, which part there is a more density of the reef? In the far from, in the near, or in the middle?
Yeah, it's a great question. So to answer that, let me see if I can pull up this image real quick. The idea is that right past the edge, waves are decaying really quick. Because they're dissipating, for example, due to, let's see, here we go. Like these rakes, like this dead oyster, like piles up, and like if you have like this dead oyster reef in front, then behind those you don't really have wake energy. So they kind of provide some protection. So if you are here, you're protected, right? So because like waves are largely in the Intracoastal Waterway, and then they fast decline in height. So behind the first, like I would say, few meters, you're protected by waves. So right there is the sweet spot. You're protected and you're filtering along.
And the more density is located there, the more density of the reef.
Yeah, exactly.
All right, let's give Dr. Crassostrea another round of applause. All right, and everybody, next week, does anyone know who's speaking next week already? Just wait for the page to load. Next week, we are very excited to have. Oh, Zhang from Computer Information, Computer from CISE, and he's going to be talking about knowledge-infused spatial deep learning for hydrological applications in this room. So it'll be live again. All right, thanks. Thank you very much. Ciao, everyone. See you YouTubers later.